So in today's lesson, we're going to look at some definitions and what it means to state and test a hypothesis. So this is leading up to our ability to evaluate using statistics, right? A given hypothesis and decide whether or not it is true or false. So today will be mostly around some terminology. Our first objective is to be able to distinguish between populations and samples. And then, what does it mean to analyze hypotheses? All right, so let's define some terms here. A population is the collection of all data, such as responses, measurements, or counts that you want information about. Okay, so you're going to measure or collect data on every one of the elements that make up that population. Okay. A sample is a subset of that population because often it's not practical to measure or collect data on the entire population. So we collect data on a sample or subset of the population. So let's look at some examples. In the year 2000, the census there attempted to count every person in the United States, the entire population. So since we're counting every person, that would be referred to as the population. And in that survey, we sent to every household what we call short form. So every household received a short questionnaire that they were asked to fill out. Now, 1 in 6 households received a long form that had more detailed questions in it. So if we only measured that data for 1 of the 6 households in the United States, that would be considered a sample, right? We would be able to sample about 16% of the population. Still a large number, but not nearly as large as the entire population. So let's look at a couple examples, see if you can distinguish between the population and the sample. Okay, so here's the first example. In the United States, a survey of 2,182 adults ages 18 and over found that 1,328 of them owned at least one pet. Okay, so what we're measuring here, are we measuring the population or the sample? Now, in this case, it's the population, right? That represents all adults ages 18 and over United States, okay? We're trying to identify both here, population and sample. So the population would be all adults in the entire United States over the age of 18, right? That's hundreds of millions of people. The sample are just the ones that we actually administered the survey to, right? So the sample was 2,184 of those adults in the United States. Let's try another one. To estimate the gasoline mileage of new cars sold in the United States, a consumer group tests 845 new cars and find they have an average of 25.1 miles per gallon. So what is the population in this example? The population would be the gas mileage of all cars sold in the United States. Okay. But what was the sample? We didn't measure all the cars, we measured a subset of those. The sample was the gasoline mileage of 845 new cars in the test. Okay, so the sample is what is more practical to measure, and hopefully from the analysis of the data from the samples, right, we can draw conclusions about the entire population. All right, a few more vocabulary terms here, parameters and statistics. A numerical description of a population characteristic is called a parameter, okay? So if we're talking about a value that we have measured for the entire population, we refer to that as a parameter. Numerical description of a sample characteristic is called a statistic, okay? So if we're just measuring, for example, the average height of a sample of people that we measured, we would refer to that as the statistic of that sample. Now, some populations are just too large to measure, as we've mentioned. So a statistic, such as a sample mean, is used to estimate the parameter or mean of the entire population. This is very common in studies that are done using statistics. So suppose we want to know the mean or average height of all adults in the United States. Now, that would not be very practical, right? To measure the height of every adult in the United States. 330 million people. Well, some of those are not adults. So let's say 300 million to measure every adult and calculate the mean. Not practical. So what we could do, right, is calculate the mean from measuring a sample of adults. We use the sample mean or statistic to estimate the mean height of the entire population or parameter. So again, we're making a measurement and a calculation such as mean on the sample, and we use that to draw conclusions about the entire population. Right, let's look at another example here. I want you to distinguish between parameters and statistics. Okay, so for all students taking the SAT in a recent year, the mean math score was 514. So the question is the mean, that math score of 514, a parameter or a statistic? So remember, parameter is where we've measured it for the entire population. Statistic is when we measure it for a subset or sample. Well, it says right at the beginning here, right, for all students taking the SAT. This is fairly easy to do, right, because your SAT scores are graded for the most part by a computer and all the data can be easily accessed. So since the mean was calculated for all students that took the SAT, the mean is a parameter of the population. How about this example? A survey of 1,060 women ages 20 to 29 in the United States found that the standard deviation of their height is about 2.6 inches. So here's the question, right? Is the standard deviation of heights a parameter or a statistic? And the answer here is that it would be a statistic, right? Since we're calculating a sample, the standard deviation was calculated for 1,060 women, not all women in this age group. So the standard deviation is a statistic of the sample data that we measured. All right, last topic here in this lesson, analyzing hypotheses. So in statistics, a hypothesis is a claim about a characteristic of a population. So in science, right, we often write hypotheses and then conduct an experiment to determine if it's true or not. In statistics, right, we do a similar thing. And often statistics are used, right, to examine scientific hypotheses. But they don't always have to be scientific. They could be done in the realm of social studies. Now, to analyze a hypothesis, you need to distinguish between two cases here. Results that can easily occur by chance. Okay, so if we look at the statistics and say, you know, the outcome that we got could be explained by the chance that that could occur. If it can easily occur, if the probability fits kind of a normal distribution, then we could conclude that that hypothesis is true. Okay, it's like, yes, we would expect it to fall within a certain range. The other case is that results are highly unlikely to occur by chance, right? And this is often when we can state that a hypothesis is not true because the odds of coming up with the measurements or values are so low that it would be highly unlikely that the hypothesis would turn out to be true. Okay, so let's look at some examples of what this is. Here's some examples of just hypotheses. A drug company claims that patients using its weight loss drug lose an average of 24 pounds in the first month. Okay, so you can imagine we could conduct an experiment where we measured, right, the amount of weight loss in a certain number of patients for 3 months and see how close the mean of that sample came to 24 pounds. And then we could determine, yes, the claim that the company makes, it could be true, or we could say that the claim in their hypothesis is false. Here's another example. A medical researcher claims that the proportion of US adults living with one or more chronic health conditions, such as high blood pressure, is 0.45 or 45%. So again, we could survey a sample, right, of adults in the United States, ask them about what chronic health conditions they have, and see what percentage of them state one or more results. Based on that data, we could evaluate this hypothesis and say that yes, the results could easily occur by chance, or no, the results that we got are highly unlikely to occur by chance. All right, let's work through one example and then we'll wrap things up here. So let's say you roll a 6-sided die 5 times and you don't get an even number. So an example would be what I'm showing in the top right here, right? We got a 5 and then a 3 and then a 1, and then we get a 5. And then another one. Actually, that example is the opposite. Huh? It says you did not get an, oh no, that's correct, an even number. Those are all odd numbers. Okay, so we're good. So the probability of this happening is, think of it for a single roll, is 1/2, right? Because half of the numbers are odd, half of the numbers are even. But to do that 5 times in a row, we take 1/2 and raise it to the 5th power. So we get this probability 0.03125, or about 3.125%. So if you had die that were fair, in other words, they give you an even chance of rolling an even or odd, and you rolled it 5 times and got all odd, there would be about a 3% chance that that would happen. If you did it 100 times, right, about 3 out of those 100 times you would get 5 die that were not even, they were all odd. Okay, now if you do this once or twice, you may suspect, the die favors odd numbers. For some reason, these die like to turn up an odd number rather than an even number. And the die maker claims that the die does not favor odd or even numbers, right? If you want to make a fair piece of die or dice, you want them to have an equal chance that any one of those 6 numbers will come up on top. So what do we conclude when you roll the actual die 50 times and get? And we're going to look at 2 cases here. Let's say in the first case, we get 26 odd numbers out of 50 rolls. In other words, 52% of the time we get an odd number. The second case we're going to analyze is, what if we rolled the dice 50 times and 35 of those 50 rolls turned out to be odd numbers? In other words, 70% of the time when we roll, we get an odd number. Well, here's the hypothesis that we want to test against each of these 2 cases. They're independent, okay, but we're going to look at an example of each. The maker's hypothesis says the die does not favor odd numbers or even numbers. In other words, there's an equal probability that an odd or an even number will come up if you roll it enough times. So often what is done on these types of problems would be to run a simulation where you roll a die 50 times. This is kind of the experiment. Totaling the odd numbers, right? How many times when we roll it 50 does it come up odd? Okay, that would be one sample set, right? Or one data set. Now, what if we did that 200 times, right? So we had 200 different percentages of how many times out of 50 we get odd numbers. Well, let's take that to the next step here. Let's say we did that simulation, and here is a histogram that shows the relative frequency of proportions of rolls that result in odd numbers. Now, if the dice is fair, right, you would expect that about 50% of the time you're going to roll an odd, 50% of the time you would roll an even, right? So if we're rolling it 50 times, that says 25 out of 50 on average should be odd, 25 out of 50 should be even, right? So we would expect that most of the outcomes, right, are going to be close to about 50%. And if you look at this histogram, you'll see that, right? The 50% is right in the middle here. But we did have some rolls of 50 where we saw fewer odd numbers, and some rolls of 50 that we had more than 50% odd numbers. Now, we could kind of assume this is a normal curve. It doesn't match the bell curve perfectly, but I think we could argue, yeah, it's pretty close to a normal distribution. Now, if we were to do many, many more simulations, say more than 200, we would hope to see, right, that this histogram would look closer and closer to the ideal normal distribution. All right, so that's what we're starting with here in our data. Now, how can we use this data to evaluate our two questions, right? Does A prove that our hypothesis is true, or does B prove that the hypothesis is true? So we're going to look at A first, okay? 50% of the time you get an odd number. Now, where will that fall on our graph here, right? 52 or 26 out of 50 gives us 52%. So that falls very close to the center, right? We would expect if the die were fair, that the average or mean would be 50%. So we got very close to that expected mean of 52%, okay? So how would we state that? It says most of the rolls in our simulation were close to 50% or 0.5. Our result of 52% was very close to the expected value of 50%. So what's our conclusion? We would say, since our result of 52% can easily occur by chance, right? If you look at our normal distribution here, the histogram, it says around 50% is the most likely outcome that you would expect by rolling these die. So if it can easily occur by chance, we can conclude that the maker's claim is most likely true, that the die is fair, does not favor odd numbers or even numbers. Okay, so that's for part A. Let's ask the same question now for part B. It said 70% of the time we got an odd number. Now, where would that occur here? That's way out here at the far right of our normal distribution. And we know, right, once you get that far out in the normal distribution curve, you have a very, very low probability of having a sample that is that far away from the mean, right? 70% is a long ways from the mean of 50%. So in this simulation, our result, actually based on the graph, we had no cases, right, where 70% of the die rolls, or we had any die rolls that had 70% of their coming out odd or even. So our conclusion here is that since the 70% value is highly unlikely to occur by chance, right, extremely low probability, we could conclude that the maker's claim is most likely false. All right. Last topic here. So analyzing hypothesis and really how do we justify our conclusions? So if you look at this matrix, right, we have four cases. If the hypothesis is true and we decide that it's true, then we've made a correct decision, right? If the hypothesis is correct or is false and we decide that it's true, then we've made an incorrect decision. And then the same happens in the other way. If the hypothesis is true and we decide that it's false, then that's an incorrect decision. And then the last case, if the hypothesis is false and you decide that, and you also decide the hypothesis is false, and that's a correct decision, right? So our goal with statistics when we're evaluating the hypothesis is to hopefully make correct decisions and not incorrect ones, right? But we can actually determine the probability that we were either correct or incorrect. So let's go back to example B, right, in the previous page. The theoretical probability of rolling 35 odd numbers out of 50, I remember I said was very low. It's actually 0.002. So based on that, right, we concluded that the hypothesis of the maker that said the dice don't favor it, we said that that's false because it's very unlikely in many samples, right, that we would get 35 out of 50. So there must be something wrong with the dice. Okay, now let's say we said that that the hypothesis was true and we decided that it was false, as we did in the case B. What's the probability that we're wrong? Well, it's about that 0.02%. Okay, so as we move further into the next lessons here and we start to apply statistics to determine whether the hypothesis is true or false, we can also quantify, right, what the likelihood is that we either made the correct decision or the incorrect decision. But all four of these cases are possible in any given analysis that we're doing. All right, so that's it. We know how to distinguish between populations and samples, and we know how to analyze hypotheses.